Hi there. Thanks for joining us on this Q&A edition of Space Nuts. Andrew Dunkley here, your host. Hope you're well. Coming up on this particular show, we're going to be focused on black holes. We got two questions independently that basically ask a similar thing about black holes and magnetic fields. And I think we've had similar questions in the past, so we'll tackle that one probably again. We're also going to look at different kinds of stars, how many of each there might be, and do those proportions agree across galaxies? And if it's different, why? Personal projects. Someone wants to know what Fred's favourite personal project has been over the years. Oh, gosh, that goes back. Well, when Galileo and I were sitting on the beach, we'll find out. And Rusty has asked why fog bows are white. That's all coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And here he is, Professor Fred Watson, astronomer at large. Hello, Fred.
Hello.
I believe when you were sitting on the beach with Galileo that you were talking about the gravity of world affairs.
We were drinking a cup of gravity each, actually. It was really nice, yes.
It's good stuff, that. It's good stuff.
Gravity.
How are you going? You good?
Yes, well, thank you. And good to see you too. I hope you're well as well and taking your gravity seriously.
I think we have to sack our laundry. We're both wearing the same shirts as last week, so it's
are we?
a bit of a worry.
It is shocking, isn't it? Yeah, I should have...
yeah, it's not good.
Yeah.
Well, we could stretch that joke for a long, long time, but we're not going to.
No, that's probably not really worth it. And probably nobody would have noticed had you not mentioned that.
Probably not. No. The ladies would probably notice before the men. My wife notices things about my attire that I don't even think about. So, yes, it's another story. That just shows they're so much more fashionable than we are. Shall we do some questions, Fred?
No, let's just end the show. That's probably easy for us. Yeah. Just
that was quick and easy. Until next time. How about we talk about black holes and magnetic fields? This is a question from Robert, and I'll follow it up with a text question we got from Lachlan. Here we go.
Hello, Fred and Andrew. This is Robert from the Netherlands. I have a question about black holes. One of my favorite subjects. At least it's not dark matter, right? Apparently, black holes do not have a magnetic field because they suck in everything, every photon, everything gets sucked into the black hole. However, we do see these enormous jets being ejected from quasars, hundreds of thousands of light years long. And obviously, they do have some sort of poles. Now, these poles, the only time I see that in reality is with neutron stars, white dwarfs, the Tauri stars, that sort of thing, and it's always due to a magnetic field. So how can this be? Maybe black holes do have a magnetic field, and the circumstellar disk around it would be able to create such a thing. However, that would not be responsible for poles on the object itself, I would think. However, maybe I'm wrong. So what do you think, guys? Does my theory have any holes in it? Or is it a hole in one? Love to hear it.
Oh, dad jokes from all corners. Thank you, Robert. And in conjunction with that, we got a text email, a quick one from Lachlan saying, is black hole radiation the electromagnetic field? This seems to be a point of contention. We've had a lot of questions about black holes, but this one seems to come up semi-regularly, Fred.
Yeah, it does. And it's kind of connected with, if I remember rightly, it's called the no-hair theorem, which I really like, actually, the no-hair theorem.
Yeah, I'm sure you do.
Which is that there's only a few parameters that you can learn about a black hole. And I did write about the no-hair theorem in Cosmic Chronicles. I should read it again and find out what I said. But yes, because there's just a very few parameters. And the idea of magnetism is that magnetism isn't one of them, which is kind of what Robert is alluding to. So if you have a no-hair black hole. The fact that there's no hair there tells you that there's no magnetism. However, black holes clearly do have magnetic fields, because that is what focuses the jets of radiation and material that are exactly the cause, as Robert alluded to, of quasars, active galaxies, delinquent galaxies, I sometimes call them, because they're all youthful galaxies. We're looking back in time a long way and seeing these quasars. So there is clearly some way in which magnetism can occur, and you basically, what you do to get the magnetic field of your black hole is you rotate it. So it's got to be a rotating black hole, and give it an electric charge. And those two things together, an electric charge and angular momentum, which is just a fancy word for rotation, produce what is known as a Kerr-Newman black hole, Kerr, Newman black hole. A Kerr black hole is one that rotates. I think a Newman black hole is probably one with electric charge. One with both of those things is a Kerr-Newman black hole, and it does have a magnetic dipole, which tells you it's got a magnetic field. So yes,
all right,
a black hole can have a magnetic field.
All right. And Lachlan's question, is black hole radiation the electromagnetic field? That's a somewhat different angle on it.
It is. But that's partly true, because what happens is that, you've got a Kerr-Newman black hole that's got a strong magnetic field. It's got an accretion disk of material around it, stuff that's being gobbled into the black hole. That material is swept up, or some of it is swept up by the magnetic field and squirted out at the poles of the black hole, the rotation poles, to make these jets of material, which themselves also generate radiation, because you've got highly energetic particles moving through, a medium, a non-vacuum medium. And so, yes, the jets are basically the radiation that arises because of the magnetic field of the black hole.
Okay.
To answer Lachlan's question.
I think so, yes.
Yeah,
but I don't really know.
Neither do I. I can't remember what it was.
We just get so many questions about them. I note that there's been a new image released of a black hole at M87, which was revealed in the last few weeks, actually. So they got a bit of a better understanding of it from the image, its environment. So, yes. And that was, I think, was a James Webb image, if I remember rightly. But yeah, that's we're starting to get more and more information about them. So there'll be maybe more of their secrets will start to be unravelled. Or was it Sagittarius A star that we're talking about? There was one that they published information about earlier this year.
It was the 28th of March, and it is Sagittarius A star. So there is a marvellous rendering. And again, it comes back to something we talked about in the last, main issue of Space Nuts about polarized light, how you detect magnetism via polarized light. The Event Horizon Telescope collaboration, which looks at the structure of black hole accretion disks, has indeed detected the polarization of that donut-shaped disk around the black hole at the center of our galaxy. And it's a picture that you can find online. It's pretty easy to find, but dated 28th of March this year.
Space.com is a good place to start, but there are plenty of articles on it, but space.com. Thanks, Robert, and thanks, Lachlan. I hope we helped you out there. Let's move on to our next question. This one comes from Pete.
Hello, Fred and Andrew. This is Pete Ellinger from sunny Sheffield here in the UK. I have 3 questions for you, all related to the mnemonic "Oh, be a fine girl, kiss me," which I use to remember the different types of stars. Question 1. What are the proportions of these star types in the Milky Way? Question 2. Do these proportions hold true for all galaxies? Question 3. If the proportions are different across the universe, what does that tell us? Thank you for the great show, which is all the better for splitting out the Q&As into a separate recording. All the best, Pete Ellinger.
Pete, it is lovely to hear from you. Thanks for the endorsement on doing 2 shows a week instead of 1. It seems to be well accepted, so that's good. Different kinds of stars, yes, we know there are. How many of each in the Milky Way? Do those proportions correlate across galaxies, and if they're different, why? I think that's a précis of his entire question load.
It is, that's right. So, what we're looking at here is the Oh Be a Fine Girl, Kiss Me is well known. Actually, these days it is also Oh Be a Fine Guy, Kiss Me. It was a mnemonic that was conjured up back in the day for what we call the spectral classes of, just a minute, let me deal with this. Can't find the phone. That's no good. I'm not going to take that. Get rid of that. Yes, sorry about that. I don't know who that was from. Somewhere.
Probably trying to sell you cladding or solar panels.
Yeah, well, they're in Queensland, so it could be either of those, as you can tell from the area code. I do apologise for that. Apologise to all our listeners. I meant to put the phone on silent, and I've clearly forgot.
I actually forget to do it on the radio sometimes, so yeah, I can sympathise.
Yeah,
but I won't.
So we were, unless it was somebody responding to my exhortation, "Oh, be a fine girl, kiss me." It could have been that, I guess, coming in by phone. But it's a mnemonic for the spectral classes of stars, and the reason why it's so totally counterintuitive, why isn't it in straightforward alphabetical order? Is because it goes back to the very early days at the beginning of the last century of people doing this spectral classification, working out what the different kinds of spectra of stars meant. So when you look at the spectrum of a star, you get this barcode of information, and they're different. And we now know a lot of the difference depends on temperature. Some of it depends on age. These are all factors that are in that. And so they did classify them originally A, B, C, D, E, F, G, etc. And then eventually it was worked out what it was that these things were telling you. And it's now in temperature order, going downwards. So O stars are the very, very hot ones, surface temperatures 20, 30,000 degrees Kelvin. Down to the M stars, the me of the mnemonic, so O, B, A, F, G, K, M. M stars are the red dwarfs with surface temperatures region of 3,000 degrees Kelvin, that sort of temperature. And so that distribution has been, we know that those are the classes. And Pete's asking, and I, Pete, fellow Yorkshireman, Pete's asking about what the relative numbers are of those. And it's pretty easy to find them on the interweb.
I just did.
Good. So you can answer that question. The bottom line is, the essentially that OBFGKM is, I missed out the A, I think, is an order of decreasing temperature, and it's order of increasing numbers, because the O stars are the rarest and the M stars are the commonest. In fact, they're by far the most common type of stars in our galaxy. So
and ours is ours a G?
It is. It's a G star. Is it? Yes, that's exactly.
So they sort of rank in the middle to higher end of numbers.
Yes, but they're not nowhere near as common as M stars are.
Yeah, M's accounting for 76.5% of all stars, and G is 7.6. So it's a lot less.
Yeah, whereas O stars are rarer still, aren't they?
Yeah, 0.00003% of all stars.
There you go. Yeah. So that's the perfect answer to the question. You see, you don't really need me. However, you might need me for the
next part.
Rest. Yes.
Yes.
Which was about whether, the same is true for other galaxies. And there are subtle differences. Basically, it's the same distribution, but there are some subtle differences. And Pete's next question was, if there are differences, what causes them? And it's things like differences in the amount of metals which are in those stars. So metallicity, the amount of iron in a star. Although, as you know, Andrew, astronomers think of everything except hydrogen and helium as being a metal, which is a bit comical. But anyway, so the metallicity can vary in a galaxy, and that would give slightly different numbers, but really only marginal. By far the commonest types of stars in the universe are M stars, these M dwarf stars. Type M, the M of Kiss Me.
Yeah, indeed. Easy to find on the internet if you want to have a look at those various star types and their, all their statistics, their vital statistics, I think would be the best way to describe it. Pete, thank you. I love those questions because they sort of get into the nuts and bolts of stars, and it sounds like it's pretty much the same across galaxies, give or take, which is good, because that would have been, if they weren't, it would have been a much longer explanation. This is Space Nuts. Andrew Dunkley here with Professor Fred.
0G, and I feel fine.
Space Nuts.
Okay, Fred, let's move on to our next question, which comes from Michael.
Hello, guys. It's Michael from Kent in the UK. Just a question about you guys. If there was a project that you could have worked on, past or present, what would it be? And more exclusively, to Professor Watson, what project stood out for you the most that you've worked on, and why? Enjoy your show, guys. Thank you ever so much. Maybe a bit selfish, but I enjoy your long episodes because it helps makes my night shifts a lot easier. Thank you ever so much, and enjoy.
Oh, thank you, Michael. We just had someone saying, we love how you split them up, and now Michael's saying, I like them when they're long. You could save it up and just run them back to back, would be my advice, because you can do that. Personal project. I mean, for me, I work in radio, and so I haven't had direct involvement with astronomy except with Fred. But, gosh, and I think for me it'd be more space science related. I'd want to be working on maybe a mission to the moon. I would love to have been involved in, if I was old enough and clever enough, working on the Apollo missions, actually being hands-on, getting those missions off the ground. If there was some way of turning back the clock and being in the right place at the right time, that would be something I would have adored working on, probably because it was so very much synonymous with my childhood. It all started when I was born. I could send home from school to watch the moonwalk, Apollo 11 moonwalk on TV, which happened in the early afternoon, our time, if I recall correctly, on my family's black and white TV. That to me was probably one of the most inspiring things that I saw as a kid, and it's still with me today. Going down after the missions to Parliament House in Canberra with my family on holiday and walking into the foyer, and they had a glass cabinet, a glass box, and inside the box was a little claw, and on the top of the claw was a rock, and that was a rock they brought back from the moon. And I was absolutely mesmerized by that. I couldn't believe that I was seeing a rock from another world. It was just a piece of basalt, but that's beside the point. It was a piece of another world, and that just blew the lid off my brain. So if I could do anything again or do anything in the past, astronomy, space science related, that would probably be one that I would want to work on. A bit more sort of nuts and bolts than something Fred might be about to talk about. But I went over and I saw the Apollo 8 control room that they set up at in Florida at the NASA base there. Got to see the Saturn V rocket hanging from the ceiling. Got to see Neil Armstrong's uniform, his spacesuit. All of that is probably what tickles my fancy most of all in terms of space science. So that would be it for me, Michael, for sure. What about you, Fred?
Well, yeah, I mean, all that, I'd endorse all that completely. But just to come a little bit further down to earth, if I may, I do have friends who've worked on projects which really were milestone projects. And one of them is the COBE mission, the Cosmic Background Explorer, which was a space mission designed to measure for the first time the cosmic microwave background radiation. That was, I think, in the 90s. Yes, it was the 90s when that was happening. It's been superseded since then by WMAP, the Wilkinson Microwave Anisotropy Probe, and Planck, a European spacecraft that measured the cosmic microwave background. So what we're doing here is putting a satellite into space to look for the afterglow of the Big Bang, which is a pretty neat thing to do, the cosmic wallpaper, the thing beyond which we can never see, because we're looking back in time so far that we can see the glow of the Big Bang. And it's got this structure on it, which was imposed on it by sound waves in the early universe. That's the really, almost spooky bit of this. But the colleague I had who worked on that, I always thought, what a way to start your career. I think it was his PhD topic. He was part of the COBE team and did a lot of work on that. He's now an astrobiologist, so he changed tack completely. And then the other one, it's a similar sort of thing, an epoch-making discovery. And maybe there are two, actually. One would be, imagine being part of the team that first detected gravitational waves back in 2015. At LIGO. You'd really be absolutely blown away by the fact that for the first time you've detected a gravitational wave from, in fact, I think it was neutron star collisions, that first one, if I remember rightly. It was... It's a date that I can easily remember, 14th of September 2015, because that's Marnie's birthday. So it's always stuck in my mind that it was on her birthday. And the other one, I guess similar, because it involves a huge, huge collaboration. It would have been great to have worked on the Event Horizon Telescope to produce that very first picture of a black hole Event Horizon, the one from M87 just a few years ago as well. So those are really big ticket projects, which it would have been great to work on. The big projects that I've worked on, in a way, the one that I had most to do with it was actually my project, which was developing wide-angle spectroscopic instruments for the United Kingdom Schmidt telescope, which is a wide-angle telescope, 1.2 meter diameter aperture. And I built 3 generations with a lot of help, of course, of fiber optic instruments. Was it 3 or 4? It was 3. The 4th generation was actually nothing to do with me, but I was kind of cheering it on. So what that meant, using this fiber optic technology, was that you could measure the spectrum of many objects simultaneously, up to 150 in the end. And we, in fact, it was 4 generations. The 5th generation was the one I wasn't involved with. So I did a lot of work on this. The 4th generation one, we did surveys of stars in our galaxy, 500,000 stars, and also surveys of about 160,000 galaxies. We made a map of the nearby universe with these galaxies. And those 2 surveys were also big projects that I worked on. One was called the 60F Galaxy Survey, 60 FGS, which wound up actually in 2003. The other was the RAVE survey, the radial velocity experiment, which wound up the observing wound up in 2013. So they were big projects, which gave me a lot of angst, I can tell you. That's why I've got this hairstyle here. But nevertheless, they were also very, very rewarding and, made me think. I think they did quite a lot for my astronomical street cred, both of them.
Yeah, indeed. Another one I remember, and you and I did a little documentary piece on this, was the 2-degree field at Conundrums and the 2DF instrument. That was a big sort of leap forward, and it was a sort of an add-on to the existing telescope, as far as I remember, wasn't it, Fred?
Yeah. That was these things are. It's a bit like hippie. It's an add-on to the Anglo-Australian telescope, hippie, that we were talking about in the last episode.
Yeah. Yes, thank you, Michael. I hope that filled the breach in terms of personal projects that we would love to have worked on. Final question, Fred, comes from Rusty in Donnybrook. I've paraphrased this because Rusty asks questions in chapters, but I'll break it down. Why are fog bows white? Now, when I first read his question, I thought, what's a fog bow? I'd never heard the term before. I know that sounds strange, but I've never heard a reference to a fog bow before. So I had to have a close look at his photo and try to figure out what he meant. And he's talking about a rainbow effect in fog, but they're not a rainbow because they're white. They're just white. He's suggesting that it's water droplet size that might be a factor here. What are we talking about, Fred?
Yeah, so sunlight lighting up a bank of fog, and I'm surprised you've never seen one, because I used to see them a lot when I was driving to your town back in the days when I used to commute from Coonabarabran to talk on the ABC. Sunlight it illuminates a bank of fog, and if you're at a position where the sun's behind you, it forms what amounts to a rainbow. But exactly as you say, the colours are washed out. They're just white. Now, Rusty did send an image of a fog bow, which was a beautiful image. And yes, it's white, but if you look carefully, you can just see a slight red tinge on the outside of it and a slight bluish tinge on the inside of it. And those are the colours that you see in a normal rainbow. So it's a kind of rainbow, but with the colours washed out. And that's exactly what's happening. And Rusty is perfectly right. It's all to do with droplet size. So fog bow droplets are much, much smaller than raindrops that form a rainbow. The raindrops forming a rainbow could be 0.5 millimeter in diameter. The ones for a fog bow are much smaller. It's an aerosol almost, where you're talking about 50 microns or something like that, rather than 0.5 millimeter. So much smaller. So there is a rainbow effect. Rainbows are caused by refraction and dispersion of light in a globe of water, dispersion being the spreading out into the spectrum. That happens in a fog bow droplet as well, but because they're so small, it's swamped out by another effect called diffraction. And diffraction is to do with the wave nature of light. Because these things are so small, you've got to take the fact that light is a wave motion into account. And what it does is it just washes out the colours. So for every colour, rather than being a single colour in a specific part of the rainbow, just gets washed out to be much broader. So the colours are all there, but they're swamped by each other until they become white, exactly like, if you're pushing it back through a prism, all these colours, they would turn white. That's not the reason. It's because of diffraction spreading out the beam, but they look white. So lovely photograph from Rusty. We should put that one on the website, I think.
I will send it to Hugh so that he's got something to do. Yeah, I'll do that.
Good on you, Hugh.
Yes. Thanks, Rusty, and always good to hear from you. Rusty often sends photos through of his astronomical images, and he gives me photographic tips. I haven't tried them yet, but I will when I get into some dark space. It's a bit too much light around my new place, so I don't have much luck with astrophotography in my backyard. But fog bows, yes. I can't believe I've never heard that term before. Maybe I was just so ignorant to it, it never stuck in my brain, which is basically my entire education. So Thank you, Rusty. Lovely to hear from you, and Michael and Pete and Lachlan and Robert. Thanks for sending your questions in. And don't forget, if you've got questions, we'd love to get them from you. Send them in right now. We'll wait. Or we'll look later. You can send them via our website, spacenutspodcast.com or spacenuts.io. Just click on the links on the page and you can send us audio or text questions through the AMA tab, audio questions through AMA, and the send us your audio question on the right-hand side under that weird purple colour. That's it, Fred. Thanks again so much. Lovely to catch up. We'll see you soon.
Sounds great. Take care, Andrew.
You too. Fred Watson, astronomer at large, and thanks to Hugh in the studio for not asking us any questions at all, ever. And from me, Andrew Dunkley, it is goodbye until next time on Space Nuts. See you then. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.